when and how ionization happen. We also don't know what produced the ionizing photon. So we know stars and quasars, AGN in general, produce ionizing radiations, but the precise mix of these sources, it's what are the main drivers of ionization is still well not known at the various epoch. And of course, the other big question is how ionizing photons manage to escape from the sources themselves into the intergalactic medium. And I think Pratika also touch upon the escape fractions briefly today. And so all these questions are tightly linked also to the topology of ionization, so the spatial distribution of the first ionized regions and how they evolve with time. Because of course, if the main drivers of ionization, for example, are the very faint sources that are more homogeneously distributed in our universe, and of course you will have a smoother ionization process compared to a scenario in which maybe it's the brighter sources or is the AGN that actually dominate the ionizing budget. And so in my lectures, I will first touch upon some observational probes of the intergalactic medium. So I think this is a bit complementary to what the previous speakers have shown, although you will see there is some overlap. So what we know about the timeline of ionization from actually an observational point of view, and also what we know about the topology of ionization, again, from an observational point of view. So what we are doing to find the first sources, the first bubbles, as we call them. And then I will talk specifically about the energy budget of ionization, and specifically I will talk about what we know observationally about the ionizing photon production efficiency, so how how sources are efficiently producing this ionizing radiation and how efficiently this ionizing radiation can escape from the sources, again, from an observational point of view. And in the last part of my lectures, so probably tomorrow, I will also talk specifically about the JWST spectroscopic capabilities and what we can derive through spectroscopic observations about the properties of galaxies. So, for example, diagnostics of AGN versus star formation, metallicity, ionizing conditions, and so on. So this is all tightly linked because, of course, we want to better characterize those sources that actually are the drivers of ionization. So again, you've probably seen this plot in the previous lecture. So these are just to show the competing scenarios, where you have some scenarios in which ionization goes very slow and starts very early. So this is a hydrogen fraction versus redshift. And so in some scenarios, you have an early start and a late end, but in some scenarios, you have a late start and maybe a faster end. And so in the blue scenario, ionization is more dominated by the faint numerous sources, and whereas in the red scenario, again, ionization dominated by the rare bright objects. So we will try to see, first of all, how observations of galaxies and quasars can put constraint on a plot like this. Okay, so think about this the problem you can basically tackle from two directions. So in the first part of the lectures, I will show how we can actually set constraint on the neutral hydrogen fraction in the intergalactic medium, whereas in the second part, we will see how we can actually compute the ionizing budget of sources and then, see what this ionizing budget will produce in terms of reionization history. So there's many different ways in which you can place limits on the intergalactic medium ionized or neutral hydrogen fraction. And of course, I will not talk about the CMB. CMB also provides some global, constraint on the IGM history. I will talk more about what we can get from galaxies and quasars or GRBs. And this is a list of different probes, different methods that people are using to probe, to set some limits on the IGM. So it goes from the luminous, so Lyman alpha, you see a lot of Lyman alpha here in this list, because as I will show in a minute, Lyman alpha is a very sensitive probe of neutral hydrogen. So you can derive constraints from the luminosity function, the equivalent width fraction, and so on. So I will go through all these in details and also leave some references, some literature that they can go and look up for each of these different probes. So just to anticipate what we know at the moment, these are current results. Again, is the neutral hydrogen fraction on the y-axis versus redshift, and you see lots of points with lots of errors. In some cases, these are upper limits or lower limits. Well, but what one can say is that currently, although we have lots of points in this plot, we really don't know, which kind of curves goes better through the data points, okay? And so we have, all in different probes give us different results, or even the same probe give different results when, interpreted by or derived by different groups because the techniques are different. So it's kind of scary, this plot, because there's a lot of work that's gone here. But I think it shows basically that we still, need to do more work to set tight constraints and actually get the various probes to agree with each other. So first of all, let's say something about Lyman alpha. So Lyman alpha emission is a key probe of reionization, and it can originate by several mechanisms. So in the ISM, it's produced by young massive stars. So star formation essentially gives rise to Lyman alpha, and also IgN emission, ionization. But also in the circumgalactic medium, there are several other mechanisms that can contribute to Lyman alpha, for example, fluorescence or enfolding gas, and also shock heating. The cross-section of Lyman alpha is very high at the frequency of the transition. So the Lyman alpha photon is emitted, the emitted photon is immediately reabsorbed by a nearby neutral atom. But because it has this broad, and then another Lyman alpha photons can be re-emitted, but because it has these broad wings, so the cross section is very, it goes very low in these wings. So during emission and absorption, if the photon can shift in frequency, the photon can actually go in the wings of the cross section, and then they can escape and be emitted by the nebula. So during these shifts, many shifts, the photon can not only move in frequency, but it can also move spatially. And so that's why the Lyman alpha can be spatially more extended than the UV emissions. Of course, during any of these shift or any of this scatter, the Lyman alpha photon can find, for example, a dust and can be destroyed. So the emergence of Lyman alpha in emission in star-forming galaxy is very complicated, because, of course, it's complicated by the presence of dust, the presence of neutral gas, and the presence of, and also the geometry of the various components, and also the presence of outflows and inflows. So, for example, in general, we know that the profile of a Lyman alpha is like this one that is shown here is very asymmetric. This is due to the fact that there are outflows normally. And I will not go into detail in this, because only full radiative transfer can really establish if and how the photons, the Lyman alpha photons in a galaxy can emerge, so can be observed outside the galaxy. And so, in fact, when we go and observe galaxies, even at low redshift in Lyman alpha, we see that there is really a wide variety of profiles. So these here to the left are low redshift Lyman alpha, low redshift galaxies that have been observed with COS and HST, and you see that the third galaxy, Lars 14, is a Lyman alpha emitter. It has this very asymmetric profile. The galaxy in the middle has a Lyman alpha emission, but also like a deep absorption. And then the galaxy to the left doesn't show any Lyman alpha. And this is due to different conditions that are present in galaxies. And to the right, we have galaxies at redshift 4. Again, you see that some galaxies have Lyman alpha in emission, some have absorption and emission, and some in absorption. Again, just only with the radiative transfer, you can really establish if a galaxy will have Lyman alpha and observable or not. Here are some examples also of the other thing that we're saying. So the fact that Lyman alpha is often very spatially extended. These are Lyman alpha emitters, again, in low redshift and in the intermediate redshift. And these images are Lyman alpha. They just show the extent of Lyman alpha compared to the UV photons, so say at 1,500 S-frame emission. For example, here in the Lyman alpha blob, you see the green is the Lyman alpha photons, and the red and blue are, where the star formation happens. So it's the V and B band. So Lyman alpha really, scatters off to much larger, spatially much larger areas compared to the size of star formation. So this is for what regards a galaxy. So the ISM and CGM shape the way that, we see Lyman alpha from a galaxy. But why is Lyman alpha important to probe the epoch of ionization? Because as we enter the epoch of ionization, so as we enter an epoch where the IGM, the intergalactic medium, is not completely ionized, but there is also a lot of neutral hydrogen, the Lyman alpha photons that escape from the galaxy can be further suppressed by the neutral hydrogen also in the intergalactic medium. So down to redshift, say, 4, 5 before the epoch of ionization, so sorry, after the epoch of ionization, when the intergalactic medium is completely ionized, we will have that, some galaxies show Lyman alpha, some galaxies don't show Lyman alpha, and this depends on average on their physical properties, on the distribution, as I said, of gas and dust. But as we enter the epoch of ionization, there is a further effect. So Lyman alpha from a galaxy that is surrounded by the neutral intergalactic medium will not be transmitted. So this guy in the middle, you see, is a galaxy in the neutral hydrogen. The Lyman alpha from this guy will not be transmitters, whereas the galaxies that reside in ionized regions, their Lyman alpha, if it manages to escape the interstellar medium and circumgalactic medium, can manage also to escape to us and is transmitted, and so we observe them. So basically, this means that during the epoch of ionization, something changes in the way we see Lyman alpha from galaxies. Okay, so and the neutral IgM not only impacts the transmitted fraction of Lyman alpha photons, but also alters their profile and their spatial distribution. So this tells you already that the flux, the Lyman alpha visibility, so the way we see Lyman alpha, the blind profile and the clustering all depend not just on the galaxy properties, and these are more or less the same, say at redshift 5 and 6, but also on how the intergalactic medium has changed. And this is the reason why Lyman alpha is such an important tool to study the intergalactic medium during the epoch of ionization. Oops, what? Okay. So the first constraint I will talk about are constraints that we can get from the Lyman alpha luminosity function. Now, just a few words on how we determine the Lyman alpha luminosity function. So here is a spectrum of, say, a redshift 3.4 galaxy with its Lyman alpha. You see the green line at 1,216 angstrom is the Lyman alpha. It's the Lyman alpha. So you have the spectrum of the source, and if you observationally want to select the Lyman alpha emitter, so a galaxy with strong Lyman alpha at a certain redshift, you can use a narrow band filter that is centered exactly where you expect to find Lyman alpha. So in this case, for example, it would be centered between 5,400 angstrom and 5,000 and say 500 angstrom. Okay, so you have a small filter. The other filters you see, U, G, R, I, will serve as probes of the continuum from the source, and this galaxy will be very bright in the narrowband filter, brighter than in the broadband filter. So you can basically select in this way galaxies that probably have Lyman alpha emission. Okay. So in this respect, the Silver Rush program, so this is a big program that was done with the Subaru telescope in the last few years. They have used this technique to actually identify 20,000 Lyman alpha emitters from redshift 2 to 7.3 in a very, very large area. So they have basically observed a large area in the sky, and they have all these narrowband filters that you see in this figure here at different wavelength to select basically Lyman alpha emitters in some very narrow redshift beams. So for example, 7.3 will be the very reddest filter you see here, which is called narrowband 1010, okay? And so they have selected lots of Lyman alpha emitters in this very large area. And so this is here is the redshift distribution of this. Of course, in this way, with this technique, you select photometric candidates, but you have to go then and do spectroscopy to confirm that what exactly is the redshift of the sources. And they have also confirmed the redshift of the sources. So they are really Lyman alpha emitters in the redshift, say 2.18 more or less, 3.3, and so on, depending on which narrowband filter they use to select the sources. And with this, they then went to derive the Lyman alpha luminosity function. So this is basically the luminosity function, I guess all people know, but I mean, is this statistics that you use to understand what is the space density of sources at a certain redshift per a certain co-moving element in a certain bin of luminosity. So here, as you see, the luminosity function versus the flux of Lyman alpha. And so these are, the various luminosity functions in the different colors are the different redshifts bin that this program has done. So you see, one notable thing of this plot is that the error bars are, for the first time, very small. So you can really, for example, understand that the luminosity function at redshift 7.3, which is this red curve, is quite below the other luminosity functions. So it's quite below the luminosity function, for example, redshift 7, 6.6, and so on. This means that basically the space density of Lyman alpha emitters drops beyond, say, redshift 6.57, okay? This is what this luminosity function tells us. This is a very great study because, as I say, it's the first time that the people were able to do derive such luminosity functions with such a large number of objects, and also spanning quite a large range of luminosity. You see, they go from 41 to 44. So that's really a wide range of luminosity. And so how do you probe, say, reionization with the luminosity function? Well, here I show you the luminosity function of the UV photons. So the blue is the luminosity function of the UV photons. These are not Lyman alpha, but these are the UV at 1,500 angstrom. And the luminosity function of, so this is actually not the luminosity function to the right, but it's a space density of, say, the density of photons, of Lyman alpha photons, okay? So what you see here, it's basically the fact that the ratio between the UV photons and the Lyman alpha photons stays more or less constant, actually reaches a peak at redshift around 6. You see that at redshift around 6, the 2 points, the blue and the red, are the closest one, which means that basically you have more Lyman alpha per UV photons, okay? What does this mean? This means that in general, galaxies at redshift 6 have a lot of Lyman alpha. So you tend to see Lyman alpha from, many sources, okay? More, for example, than at redshift 2, because you see at redshift 2, the blue and the red are actually more far apart, okay? And then the luminosity function of the density of UV photons actually declines smoothly below redshift 6. This tells you that the galaxies, the UV photons from galaxies, they tend to decline slightly, okay? There is less galaxies, less luminous galaxies. But the luminosity density of Lyman alpha actually basically falls very, very abruptly, okay? So this means that at redshift above 6, the UV photons decline a bit, but the Lyman alpha photons actually, fall to, very small. And this is the effect of reionization, okay? So this abrupt decline and the fact that the two curves, they separate very wisely, it's basically an imprint of reionization. Because the decline of the UV photons basically tells you something about galaxy evolution. So it tells you that the galaxy, the density of galaxy, the density of luminous galaxy goes down a little bit as we go to higher redshift. Basically, you have less galaxies, they are less bright. But the decline of the Lyman alpha cannot be due to galaxy evolution because it would not be so abrupt. And this is precisely due to the intergalactic medium. The fact I was telling you before, so that you have at a certain point, you start to have neutral hydrogen in the intergalactic medium around the sources. The neutral hydrogen does not prevent the UV photons from being transmitted, but it prevents the Lyman alpha photon. And that's why the Lyman alpha falls so much, okay? And of course, you have to, model this, you have to do some modeling to, go from these numbers, so these UV densities, to, determining how much neutral hydrogen in the intergalactic medium you need to have this fall of the Lyman alpha photons. And this is precisely what modelers are trying to tell us. With the same survey, actually, people have tried to constrain also the Lyman alpha clustering. And so here, these actually are simulations where you can see that depending on the distribution of the neutral and ionized gas, the intrinsic distribution of Lyman alpha emitters will be, actually mapped into a different observed distribution. Okay, so think about, for example, in the first, the rightmost panel. Okay, you have a lot of where you have neutral gas. Okay, it's a black region. You will not have Lyman alpha emitters. So even if you have Lyman alpha emitters, intrinsically you will not see the Lyman alpha emitters. You only see Lyman alpha emitters where the ionized the gas is already ionized. So, for example, in the leftmost column, there's this top region that is white, and this is precisely where in the bottom panel you see still Lyman alpha emission. So in the rightmost panel, we actually have a universe that is almost completely ionized. You see all the map above is almost completely white, and so this is the same from, so you will see a lot of Lyman alpha emitters, apart from this small region where you have a blanketing because the gas is still neutral. So basically, this picture, this is from simulation, tells us that the clustering of Lyman alpha emission will be also a sensitive probe of the distribution of neutral and ionized gas. Okay, again, the only survey that currently has large enough area where you can actually probe, Lyman alpha clustering is Subaru. Is this Silver survey done with Subaru? Subaru has a very, very large camera where you can, where you can observe very, very large patches of the sky. So in particular, this survey was done, for example, in Cosmos and XCS. These are very large areas where you can that you can observe. These are prime extragalactic field, and so this is currently the only survey that tells us about the clustering signal of Lyman alpha emission. And here are some results from MEDA 25, and they could derive quite accurately the clustering of Lyman alpha emitters, but just up to redshift 6.6. So these things really still have not gone to the highest redshift. So, for example, still at redshift above 7, we don't have really surveys that can probe the clustering. And so what these people have done is combining a luminosity function and clustering constraint, and they have derived the neutral hydrogen fraction at redshift 6.6, 7, and 7.3. So these are some numbers. So, for example, they derived at the redshift 7, they only have about 20% neutral hydrogen, whereas redshift 7.3, the neutral hydrogen fraction is already 75%. So you see it's a very rapid change. So in these surveys, what they derive is that the process of reionization is very, very rapid, because as you see, the change is very rapid. So another complementary way is to derive a neutral hydrogen fraction is through simply compute the fraction of galaxies, star-forming galaxies, the Lyman break sources, which are generally star-forming galaxies. So you basically compute the fraction of Lyman alpha emitters in all the star-forming galaxies. So basically what you do is observe all the star-forming galaxies, and then you say, okay, how many of these sources have Lyman alpha in emission? And so you set some threshold for Lyman alpha emission, and then you say, okay, what is the fraction of sources that have Lyman alpha emission? And so here are some results. So if you follow the red points here, you see that this is the fraction of Lyman alpha emitters from redshift 4 to 8. So now you have an ensemble of sources, which is not just Lyman alpha emitters as in the previous studies. This is all star-forming galaxies. And these studies tell us that if you take all star-forming galaxies at redshift 6, about 60%, or sorry, 45% of sources have Lyman alpha emitters. Remember that Lyman alpha is not a simple line, so fact that only 45% of galaxies show Lyman alpha emitters is because you have dust, you have neutral gas inside the sources, so not all the sources will show Lyman alpha. The red points show an increase from redshift 4 to 6, and this is probably due to galaxy evolution. As I told you, you have more probability to have Lyman alpha in emission if you have less dust, right? And so as you go to higher redshift, your population of sources will be, maybe younger, so maybe they will contain less dust, so they will emit more Lyman alpha. And then you have this decrease, and again, this decrease is due to the increase in neutral fraction in the intergalactic medium. So this was the situation, say, until before JWST. We had this kind of quite nice, clear picture that, the Lyman alpha fraction was rising from redshift, say, 3 to 4, 5, and 6 because of galaxy evolution, and then it was decreasing because of the intergalactic medium neutral content. Again, of course, to pass from this rise and fall to an actual constraint on the neutral hydrogen fraction, we needed to go through modeling and through maybe simulations, because basically we needed to understand what neutral hydrogen in the IgM was required to produce this rapid fall of the Lyman alpha fraction in galaxies. Unfortunately, with the JWST, despite the fact that we actually have so many new observations, the situation is now a bit less clear. So like these are some results from JWST. These are some Lyman alpha emitters. You see the Lyman alpha emitters at redshift, even very high redshift. We even have, so these are redshift 7 sources. And this is a Lyman alpha statistics after, this is actually an old plot now because it was made at the beginning of, end of last year. But we have lots of observations of Lyman alpha. And some are actually very surprising, because if you think that beyond redshift 7, the intergalactic medium is very, very neutral, then you should not expect so much Lyman alpha, to see so many Lyman alpha emitters at redshift above 7. But actually, this was not the case. So JWST has actually revealed also Lyman alpha emitters at redshift, a quite high redshift, even at redshift 13. So this galaxy here from Wittstock it's a redshift 13 source, which actually shows Lyman alpha. This was very unexpected, because we did not think that there would be so much Lyman alpha. So of course, we expected some emitters, but we expected that the fraction of emitters would really decline to almost 0. And so, these are the new plot when you consider the fraction of Lyman alpha emitters in general star-forming galaxies. This is divided by so in the left plot you see, in the upper left plot you see this fraction of emitters versus redshift, and you see that you don't see this very nice rise and fall that was what we thought was the true before JWST. And we now see that the fraction depends a lot on MUV, depends on which equivalent width limit you employ. So the situation is much more complex. And we also realize that depending on which field you look at, the fraction of Lyman alpha emitter varies a lot. For example, here in this plot by Napolitano 25, we have the fraction of Lyman alpha emitters in different fields. So just look at the blue point and the yellow point at redshift 7. This is the fraction of Lyman alpha emitters, respectively, in the EGS field and in the UDS field. These are simply two fields, different parts of the sky. In one of the fields, you see a lot of Lyman alpha emitters, and in the other field, you don't see Lyman alpha emitters. So this basically tells you that there is a lot of field-to-field variations, and so basically the process of reionization is definitely completely inhomogeneous. Okay, this is, I mean, we knew a little bit that this was the case, but now with the new observations, they've really probed that the fraction is very different in different fields. So again, in any case, now not considering these challenges, to pass from these fractions to the visibility of Lyman alpha emitters to a neutral hydrogen fraction, you still need to pass from modeling, detailed modeling of these distributions. So, for example, this is another constraint that was obtained by the Yates team at redshift 7. They derive a 60% neutral hydrogen fraction. So, as I mentioned already, there is a lot of challenges in the use of Lyman alpha fraction to infer the neutral hydrogen in the IgM. So, First is these large field-to-field variations that we are observing. Then there is also the fact that in local, there are, in some cases, we see that in these small fields, you actually have some local ionized regions that then influence the statistics. And I will talk a little bit more about these bubbles later on. Unfortunately, so far, most of the JWST observations have been obtained with low resolution, which means that we're not really very sensitive to low equivalent width Lyman alpha emitters. And I will talk about probably tomorrow about the spectroscopic capabilities of JWST. And finally, again, JWST observes these Lyman alpha emitters through very, very small, what we call pseudo slits. So JWST does not have the slit like, the ground-based spectrograph, but it opens basically these small shutters. And so in many cases, we think that because Lyman alpha is extended, as I showed earlier, we don't capture correctly, the full extent of Lyman alpha. Whereas in the ground-based observations, the one we had before JWST, the slits are generally much larger, and so we capture better Lyman alpha. So this is something we are still working on. So now we talk about a slightly different technique, which basically can be applied to both galaxies, but also it was first of all applied to quasars. It's which also allows us to get constraint on the neutral fraction. Okay, basically, so when this is constrained on the damping wing, the Lyman alpha from the Lyman alpha damping wing. So basically, if you have your Lyman alpha, you have your galaxy or quasar that emits Lyman alpha, but this source, resides in a neutral medium. You will have this, this profile redwards of Lyman alpha, which is called exactly the red damping wind, which is sensitive to the amount of neutral hydrogen present in the surrounding of the source. To model this, you need a good knowledge of the intrinsic spectrum, so either the quasars or the galaxy. If you apply this to quasar, you might be biased because, traditionally this was applied to quasars because quasars are very, I will show here, so this is a spectrum of a quasar. Quasars are very bright, and so you can model this damping wing very, very well. Okay, so for example, this is a redshift 7 quasar, so this basically the blue one is what you think is the intrinsic spectrum of the quasar, and then by seeing basically the ratio between the intrinsic spectrum of the quasar and what you really observe, which is this this black line here, you can model the effect of the intergalactic medium. Okay, so we were able to do this in quasar because they were the only objects that were where you could get a very good observations of the continuum from the ground until at least JWST. So for example, this was again, these are where the constraint the people will get a redshift 70% neutral hydrogen fraction from. But of course, a quasar is when you do this to a quasar, you're deriving the intergalactic medium, the IgM neutral hydrogen only in that particular direction. Okay. So these are the challenges again that you need to know very well the intrinsic quasar spectrum. The quasar only probes a particular line of sight. There could be, for example, DLA systems. So there could be some neutral gas inside the galaxy or the quasar itself that can also give a contribution to the red damping wing. So for example, here are to the right there are some. So these are some models where you can see that several parameters give degenerate effects, basically. But nevertheless, people have applied this technique first to quasars, so getting constraint on the neutral hydrogen fraction. These are actually the two most distant quasars known today, the redshift 7.5, and these are actually JWST spectra obtained with very good resolution. And so here again, people derive these are two quasars, one a redshift 7.51 and one 7.54. And as you see immediately that the neutral hydrogen fraction derived are quite different. So one has more or less 60%. So just look at the green lines, for example, and the other one gives 35%, I think. So this means that at the same redshift, because the redshift is very similar, but on two different part of the sky, you have very different neutral hydrogen fraction, again, telling you that, ionization is probably something very inhomogeneous. Again, this is a plot showing that you have the generacies that you have to take into account between the intergalactic medium effect and the absorbers that are contained in the galaxies themselves. This type of studies is also possible with the GRBs afterglow, because these are very, very bright sources. So you can study the lumping wing in these GRBs, and this was done in GRBs at redshift 6.3 and 6.73. And now finally with JWST, we can do this on galaxies. This was not possible before JWST, simply because galaxies are much fainter than quasars and also the GRBs. And so you were not able from the ground to detect the continuum, the spectra you could not get with such a good signal to noise to be able to analyze, the damping wing effect. Finally, with JWST, we are able, although not always we can detect the effect in single galaxies, only in the brightest sources we can. So some people, for example, are putting together lots of galaxies, lots of galaxy spectra and stacking them together. So for example, this was an exercise done a couple of years ago now, where people basically have, stuck together the spectra of galaxies at redshift 7.1, 7.44, 8.2. So you see here in the left plot, you see that, for example, the blue stack is the one at low redshift, and the red stack is the one at higher redshift, 9.9. You see that the damping wing profile really changes. So the flux is more and more suppressed as you go to higher redshift. So this was very exciting, although then, and people have tried to again infer the neutral hydrogen fraction from this type of studies. These are some results, I think, from Heinz. Again, we have constraint at redshift 5.8, 7, and 8.6. In this case, for example, we have still quite a large neutral hydrogen fraction at redshift 5.8, which is a bit unexpected. So you see, you still have reionization not completed even at redshift 5.8. The challenges are already a little bit told you. So the challenges in such type of studies is the fact that you have the dumped system inside the sources that can also have some effect depending on the neutral column density of things that are inside the sources. And again, most studies have been done with the prism, low resolution. And another, let's say, challenge is that in some cases, when you have bright sources, these sources will have ionized a little region around them already. And so these things you must take into account when doing the calculations. And so in this paper by Huberty, which is very interesting, they really talk about the degeneracy between all these various things, okay? So the presence of the ionized bubble around the galaxy or the quasar is basically, in some sense, related to how long the source has been switched on for. So if your source is already, something that has been switched on for 100 million years, and then it will have already ionized the region around it, then of course, you're not probing really the neutral hydrogen around it, but, on larger scales. And so all these things are, say, degenerate with each other. Now, now we are going to the very late stages of reionization. So when, reionization is almost complete, you have basically other types of probes that are, related to quasar study. I think Pratika talked already about the Gunn-Peterson trough, which basically allows you to determine the neutral hydrogen content. And this, I think she already showed also, this is the compendium of very high redshift quasars, and basically with the Gunn-Peterson trough, you can constrain the latest phases of reionization. So the Gunn-Peterson trough just tells you, that there is some new residual neutral hydrogen, but it's not so sensitive to it basically saturates at small value. So you just need a little bit of neutral hydrogen, and then you will see this trough. So you will see basically a blank region in the spectrum of your quasar. Another technique that people use is the dark fraction. So the covering fraction of dark pixels that is present in the Lyman alpha and Lyman beta forest can also constrain the neutral hydrogen fraction. And it's very interesting because it's model independent. It will give you upper limits, but it's model independent. So for example, here is a spectrum of redshift 7 source. And for this, of course, you need very high resolution spectra. And so currently, for example, X-shooter, which is a very high resolution spectrograph on the VLT, is one of the few instruments that can give you this type of statistics. So you basically study the dark gap. So how many pixels are completely absorbed at the very redshift. And so here to the right, you see the limits obtained. These are the latest limits obtained by June 2023. And so you see the fuchsia and the red points are those limits that you can determine with this dark fraction. And these are some of the latest results, which have been also obtained with the high resolution X-shooter spectra. So this is another example of this very, very high resolution. X-shooter has a resolution of 20,000. So you can really, probe in between these tiny lines, and you can really probe the dark regions. And so in this survey of, I think they have 30 quasars observed with very high resolution, they found that even a redshift as low as a 5.5, 5.6, you already have some, large opaque troughs. So basically, you still have some patches of neutral hydrogen at this low redshift. And so basically, they conclude that ionization is not complete until, say, 5.3, redshift 5.3, 5.4. This was also a relative surprise because from earlier studies, in particular from studies of the Gunn-Peterson trough, earlier studies on the Gunn-Peterson trough, we thought that the end of ionization was basically 6. But now we had to revise slightly this. So at redshift 6, you still have some, large paths. You need just to, there is a large field-to-field variation. Again, there is large scatter between line of sight. So going back to our, timeline of ionization, well, I go back to my previous slides, which I say that timeline ionization is still unclear. So we have lots of points. I showed you that, there is lots of different methods, different techniques to put points in this plot. But things don't always agree with each other. There's still a lot of room for improvement. Not only we need the better statistics, but we need more independent fields, because we saw that, things change very much depending on where you look at. You need high resolution spectra, high resolution and good signal to noise spectra. And I think now JWST will be able to, to do this, but we have to, do more proposals in that. And of course, we need simulations to drive the interpretation. Okay, so just before I stop for questions, I want to also show that we are also trying to set some constraint on the topology of ionization, because what we find is that even in large neutral intergalactic medium, as I showed you, Lyman alpha can be visible. And the reason it is visible is that because galaxies have already, when they are bright enough, they already carved large enough ionized bubbles. And when a galaxy has carved its ionized bubble, maybe with the help of faint sources in the vicinity, the Lyman alpha can shine even at redshift 10, when the average fraction of the neutral fraction is close to 1. And so, as I showed already, this was a big puzzle because, it's a distant, the most distant Lyman alpha emitters is the redshift 13. It's in a, at an epoch when we think the intergalactic medium should be completely neutral. And so we should not see Lyman alpha emitter, okay? So people have tried to, model this source, because not only it has Lyman alpha, but it has also damping wing. And the damping wing is indicative, as we saw before, of very large amount of neutral hydrogen. And so yeah, there are several models to model it, and so basically one model is that there is probably a lot of neutral galaxy gas in the interstellar medium, and it's very inhomogeneous distributing. And so because Lyman alpha has this resonant scattering behavior that I explained before, basically we are seeing Lyman alpha from outer parts, so the central source is not, say, seen, but the Lyman alpha can escape from the outer parts, okay? And of course, this source has already carved somehow large ionized bubble because it has been, on for quite, well, not a lot of time because it redshift 13, but at least for several tens of million years. So this is a possible model. And of course, to test this, we need maybe spatially resolved observations. We have also found other, say, bubbles, so regions where we see lots of Lyman alpha. So, for example, we also see some clustering of Lyman alpha. So we see more than one Lyman alpha very close to each other. And this tells us basically when you have an overdensity of source, the combined output from the galaxies can have an ionizing output that produces a large ionized region. So these are some very recent results. And so this is how we calculate the possible radius of these ionized regions. We have to basically compute the total number of photons that can escape from the sources, and then we need to take into account for how long such sources are on. And of course, we need to take into account not just the galaxies that emit Lyman alpha, but also the sources that maybe don't, emit Lyman alpha, because they could still provide ionizing photons. In the future, we will have constraint on the topology of reionization and the sizes of H2 regions with instruments that will try to map much larger volumes. So JWC is great to, pinpoint single regions, but it has a very small field of view. But and so in the future, we will have instruments that will try to map the spatial distribution, for example, 5 meters on much larger scales. And for European people, we have MOONS that is finally coming in a few months. And so this is, for example, an instrument that it will be put on the VLT. It has a spectrograph with a very large field of view, and it will allow to map the Lyman alpha distribution, so the overdense regions and the voids, on very large scales. And of course, in the future, of course, we have SKA. So with SKA, we will be able to map the 21 centimeter brightness and really map the reionization. So I'll take questions now before going to the second topic.
Thank you. I can repeat the question again.
So,
yeah, are there any questions?
I was thinking, because I'm not there, I can also, you can also give my email to people in case they have something that, I will give, of course, the lectures, but if people have some questions they want to ask me even later on, maybe just simply give them my email. And of course, if there are questions now, I'm happy to answer.
Yeah. Are there any questions?
We have a microphone. Questions?
Very relaxed. There's no questions so far.
Okay.
So are you happy to continue?
Yes, of course.
Yeah, we have a coffee break at past. Is the
yeah? So I will do probably not the second topic. It's less. I will stop after a bit, but I can continue tomorrow.
Perfect.
Okay.
Thank you.
Okay, so now we will talk a little bit. So as I told you, this was the approach number one, which basically was putting some constraint on this plot of the neutrality in the IgM versus redshift. But now we'll go the other way around. So we will actually start from the sources of reionization, and we will see what, if you combine the output of such sources, then what do you get in terms of, reionization history. And so again, I think Pratica has shown these equations. So these are the equations governing reionization, whereas you have on one side the ionization terms, how many, ionizing photons you have, and then you have the recombination terms. And the recombination will, is basically depending on also on the clumping factor, and this is something that I guess just simulations at the moment can tell us. So what are the total ingredients of reionization? This is how we kind of try to compute the total budget. And this is basically, this is an equation that is very important because it tells you the various ingredients. And then I will now go into details in each of these ingredients and what JWST has done to, in the progress of these ingredients. So the first ingredient is the density. Rho UV is the total density of UV photons. This is a very easy quantity that I will show you. Is a very easy quantity to measure. Basically, is the non-ionizing photons. It's a UV luminosity. Then you have the photon production efficiency, which tells you how many ionizing photons are produced per UV photons. And finally, you have these famous escape fractions, which is the fraction of ionizing photons that escape into the IGN. So the combined contribution of galaxies and AGN must be obviously considered. So I will focus very much on galaxies, but more or less the same things apply for AGN. And so the first ingredient, I put it in green because it's something that now I think, well, we can say that we have solved, let's say. So the UV luminosity density is basically, the integration, you integrate the luminosity function. Okay, so it's the integral of the luminosity times the luminosity function. So it tells you basically how many, UV photons you have around from galaxies or from AGN. And this is one of the, it's a plot of the current knowledge of the rho UV versus redshift. You see with JWST, we are arriving to redshift 14. And so what you see, the only thing we need to notice here is that, well, first of all, we have lots of points. So many people have derived the UV luminosity density. More or less points tend to agree with each other. And I just want you to notice two things. So one is the red line. The red line is the extrapolation from the pre-JWST results. So before JWST, we thought that there was a decline in the UV density, in the rho UV density, it's a smooth decline. So as we went to go to higher redshift, we had less and less UV photons, so less galaxies. All the points, all the colored points, JWST results are above this line. So this was one of the biggest surprises from JWST. We have lots of galaxies, many more luminous galaxies than we thought before, okay? Up to redshift, say, 13. And this is something that, poses some questions. It's very good on one side because we have lots of photons for ionization, but it poses, of course, a lot of troubles because, there is discrepancies with expectations and also with models. So the blue dotted line, for example, is a constant star formation efficiency prediction. And you see that basically, again, the points that are obtained by JWST tells us that, as you go to high redshift, you probably have a higher efficiency in the conversion of gas into stars. So have a lot of efficiency in the star formation. Again, I will not go into details here. So it was a big surprise. There's lots of models now that try to assess why we are finding so many sources. The important thing is that, there's lots of, the luminosity function is quite well known. And I also want to point out that we know quite well now, we're trying to set tight constraint also on the faint end of the luminosity function. So why is the faint end important? Well, you see here, these are luminosity functions at redshift 9, 11, 12. You see that they go down to minus, the magnitude of minus, say, 17. That's pretty faint. But still, it's not as faint as what you need to integrate to. Remember that the rho UV is the integral of the luminosity function to a certain minimum luminosity, okay? And the minimum luminosity is much below what we actually currently constrain with JWST. So even in the lens field, in the deepest field, like programs like NGDeep or Canucks, we go to minus 17. Even using lensing, we go to minus, say maybe minus 16, minus 15, but we never go to the minimum luminosity that, we are we think that galaxy exists, which is around maybe -13. So we need to basically extrapolate in our integration. And that's why knowing accurately the faint end of the luminosity function is important, because if you don't get your faint end well, you extrapolate wrongly, and because you extrapolate, you can have, large errors in the extrapolation. So the latest results are that, this faint end slope does not steepen, remains constant. And so, we can, well, of course, the error bars are still there, but, we're starting to see that, things converge. So there is no steepening of this faint end. So the second ingredient is, as I told you, the photon production efficiency. This is orange, because we have the capabilities with JWST now. For the first time, we have the capabilities to measure it very accurately, but we are still not converging on what is really the answer. And I will show you this. So how do you determine the photon production efficiency? Is basically the total ionizing photons dividing the total non-ionizing photons. And the total ionizing photons are taken proportional to the H-alpha luminosity, okay? Because basically these photons actually, are emitted, and then they go and, excite the H-alpha luminosity. Or alternatively, another Balmer line at H-beta. And so, for example, we know from models that the ionizing photon production efficiency here, as a function of the age of a stellar population, if these are BPAS models, so we know that the ionizing photon production efficiency is higher for very young stellar population, and it's also depends, for example, on the metallicity. So these lines, some of these color lines are from different metallicities. So, for example, yeah, the green line would be for solar metallicity. The yellow line would be for the metallicity that is very, very, very small, 10 to the -5, sorry. So, low metallicity sources in the models produce much higher, more ionizing photons at a given age. So this is what models tell us. Note that a correction needs to be made for the escape fractions, because if the ionizing photons actually escape from the nebula, and actually we know that some must escape because they go to the intergalactic medium, they will not contribute to the Balmer line, okay? So the Xi-ion is actually Lyman alpha, the luminosity of H-alpha divided by 1 minus F escape. Because this F escape is actually very low, we know that it's very low, and I will tell you about this later on, then we know that the correction is small, so we usually actually don't even make this correction. Okay, so why is JWST revolutionized our knowledge of Xi-ion? Well, because until JWST, to detect H-alpha, remind you that H-alpha is at around 6,500 angstrom rest rate. So to detect H-alpha in high redshift galaxies was basically impossible. So with the ground-based observations, you can get to around 2 microns. And so you could get H-alpha up to redshift 2, maybe H-beta out to redshift 3, but definitely not in the epoch of reionization. So definitely not at redshift 6, 7, or 8. With JWST, because of its great capability, spectroscopic capabilities, now it's very, very easy to detect H-alpha, H-beta. I mean, it's really easy. These lines are booming. Even with the short integration times, you see, these Balmer lines everywhere. So this is a spectrum of redshift 6 source. It's actually MUV -20, which is a moderate luminous source, not very luminous. So you see the H-beta, oxygen, and you see the H-alpha with a very good signal to noise. And so it's the first time that we can detect H-alpha or H-beta up to redshift 10 really routinely, basically in every source we study. And this is great, you see. So basically we can measure Xi-ion very easily in all sources. And so, for example, this is a work by Simmons last year. And so they measure the Xi-ion as a function of in many sources, as a function of redshift, and also as a function of, say, MUV. And so they found that basically Xi-ion as a modest increase, so increases slightly as you go to higher redshift. So basically this tells us that at redshift 6 and above, basically galaxies are more efficient producers of Psi-ion, which is something that, can be expected. I mean, we saw from the models that, Psi-ion is stronger for young stellar population and low metallicity stellar population. So this is something that you might expect. So as you go to high redshift, galaxies have younger stars, maybe lower metallicity, and so their production of ionizing photons is slightly higher. You see, it's not a very, it's dramatic increase. It's a smooth increase. The slope is 0.05 in this work, but I mean, most works actually agree quite well with it. So what is more debated is actually the dependence of Psi-ion on MUV. So how, if Psi-ion, the production is more efficient or less efficient in faint or bright sources, okay? This is actually very important because when we go and, if you go back to our ionizing, to the budget of ionization, we are integrating, the UV photons and then multiplying them by the Psi-ion and then again by the FSK. But so we need to know how Psi-ion depends on the MUV, okay? If it's bright, it's a more efficient, the more efficient producers are the faint sources or the bright sources. This is also important to understand which sources actually contribute mostly to reionization, okay? So in some words, for example, Yerena, Arshan, and Papovich, what they see is that there is a dependence on Psi-ion on MUV in the sense that the faint sources are the most efficient producers. So the faint sources, those around, say here we go down to minus, say, 18, have higher Psi-ion values compared to the bright sources. But this is not agreed still. Actually, there are some other works in which they actually find a more moderate slope. So basically, the Psi-ion doesn't vary so much with MUV. It's still a little bit higher in in the faint sources, but not so much. And then there's also some works like Pal and Simus where actually you almost find the the opposite, or in any case, it's a kind of definitely a flat relation, if not opposite, in the sense that again here in this plot to the right, actually the x-axis is flipped compared to the other two, so you have the bright sources to the right, and so there's no indication that the faint sources are have higher efficiency. So, well, this is probably due to selection biases. So these samples, people treat samples differently. In some cases, they start from a spectroscopic sample, in some cases from photometric sample. So, this is actually another work which has presented the photon production efficiency in two of the faintest sources actually ever observed. These are two sources between minus 15 and minus 17. And at redshift around 7, these are lens sources. That's why we can probe such faint sources. And in this case, the photon production efficiency are very, very high, almost as high as what is the natural limit, which is 26. So this study would support the idea that it's the faintest sources that have the highest photon production efficiency. But as I told you, this is something that is still definitely not agreed on. There is a lot of debate on this, and I think it's weird because, as I told you, it's very easy to measure now Psi-ion, but the results are not in agreement with different studies. So I think we need really to understand the selection bias before giving an answer. By the way, we are also now able to study the dependence on this parameter, the photon production efficiency, on the galaxy physical properties. So we have some expectation, of course, because we have the models, the stellar population models. But for example, here in this study by Irena, we found, observationally determined for the first time that indeed Psi-ion and metallicity are inversely, proportional in the sense that the highest Xi ion is found in the galaxy with the lower metallicity. And also we found that Xi ion is proportional to the specific star formation rate. So basically, the galaxies with the highest photon production efficiency are the ones with low metallicity and very high specific star formation rate. So now we go to the last and most difficult parameter of reionization, which is the Lyman continuum escape fraction. And this is, as you see, it's red. And it's red because it's basically, the thing that I don't think even with JWST, we have really not solved, okay.
So I'm just moving your video.
Yeah, okay. And so the escape fraction represents the fraction of ionizing photons, so those with energy capable of ionizing hydrogen that manage to escape from the galaxy, interstellar medium, and circumgalactic medium into the intergalactic medium. Okay, so it's the this is the one of the definitions is the intrinsic ratio. So on top you have the intrinsic ratio of non-ionizing to ionizing luminosity. So non-ionizing luminosity, you take, well, here is 1,470, but you can also choose 1,500 as long as, it's fixed. And the Lyman continuum range is in the range 800 to 900 angstrom rest frame, okay? So basically you try to observe this flux. So you have to observe the flux at 900 angstrom rest frame, and then you need to model also the intrinsic flux. So there is a part that is observed flux. So the bottom part is observed quantities, and the top part is actually intrinsic quantities. And so the bottom part you can observe. They are challenging, as I will show in the observations, but these are observable. And the top part is basically in modeling. So you need to model somehow the intrinsic spectral energy distribution of your source, okay? And so this is not only an observational problem, it's also a problem of modeling the sources. So the problem number one is that the Lyman continuum emission in galaxies is in general very faint. It's much fainter than the non-ionizing continuum. So for example, this is a galaxy at redshift 0.3, observed by Itodov some years ago. This is a COS spectrum. So it's a spectrum obtained with COS, which is a UV spectrograph on the HST, okay? And this is the enlargement here is the Lyman continuum observations, okay? So on top you have the observed wavelength, and on bottom you have the rest frame wavelength. So you see immediately that this is a bright source. Actually, it's a low redshift source. The Lyman continuum part is very, very faint, okay? So you can see immediately that the flux, the ionizing flux is much fainter than, the continuum that you see the Lyman alpha here, but you have then the non-ionizing continuum, okay? Even though, this galaxy has an escape fraction of 0.3, so 30% of the ionizing radiations is escaping from this galaxy. So the first problem is that, of course, as I told you, is that the Lyman continuum emission is in general very, very faint. So it's difficult to make such kind of observations, okay? Because in galaxies, usually only a tiny fraction of the produced ionizing photons escapes from the source, okay? Because you have the dust, you have the gas, you have effects within the interstellar medium, the circumgalactic medium. All these effects are very important. So if you have the intrinsic ionizing flux, this is blue, the black spectrum, and then you have, for example, some dust. We know that dust preferentially absorbs the blue source, the blue wavelength, and then you have other effects, and you will have this suppression of source. So and the ionizing sources, ionizing photons are more suppressed than the non-ionizing photons, because the non-ionizing photons basically are just attenuated by the dust, the dust in the ISM, but the ionizing photons are attenuated by everything that is in the ISM, including also H1, but also by everything that is in the intergalactic medium, okay? That's why they will arrive much, much fainter than the non-ionizing photons, as can be seen here, okay? So these are some observations, for example, of some low redshift galaxies. And this is actually a very important sample because it's a very large sample that has been of Lyman continuum, well, of galaxies where Lyman continuum emission has been studied in very, very details. It's called the low redshift Lyman continuum sample. And so here are 3 galaxies, a non-emitter, a marginal emitter, and an emitter. Okay, and so these are the thumbnails. These are all HST observations again. And so you see always that the Lyman continuum flux is much, much fainter than the UV continuum. So for example, for the non-emitter, we can say that this galaxy probably has an escape fraction less than, say, 0.5% or something like that. So you can set a limit on this. There is also an observational limitation. So I mentioned that these observations were done with HST, okay? And the reason is that the rest frame range of Lyman continuum is not observable from Earth up to redshift 2.5. So we cannot, because, you know, the atmosphere is luckily not transparent to UV photons, so we are protected from UV photons. Then to measure the Lyman continuum emission from redshift, say 0 or 1 sources, we need to go to space. And currently, the only instrument that is able to actually perform these observations is HST, because it has a UV channel. So JWC is very powerful, but it's basically an optical near-infrared observatory. And so it will never be able to you know, give us observations on the, you know, Lyman continuum emission from, say, low redshift sources, okay? So this is currently only HST, and actually HST is degrading its UV capability. So, you know, unless we get new instruments, we are not able to, soon we will not be able to observe these things. As we move to higher redshift, luckily the Lyman continuum range is shifted to, you know, above 3,000 angstrom, 3,500 angstrom, and is observable also from ground-based, but also, of course, great space-based observation. So even the HST can still continue. So, for example, this is a galaxy at redshift 3. It's I think it's one of these very famous leakers. It's, I think, ion. So there are so few at redshift 3 that we gave them particular names. So we named them because it's this is, I think, is ion 2. And again, this is a spectrum, I think, obtained with force 2. And you see that this is the Lyman continuum range. The flux is very, very faint, despite the fact that in this source, if you make the calculation, the escape fraction is about 50%, okay? This Lyman continuum range has been not only observed with the spectrum, but also with photometry, again, by HST. So the thumbnails in the bottom part, they are from HST. So the filter 336 encompasses exactly the wavelength range where we see Lyman continuum, and the other 2 filters encompass the non-ionizing radiation, so from the stars. Another challenge is, again, observational challenge, that when you try to observe these galaxies at redshift, say, 3, you have also the presence of interlopers. So, for example, this is a source at redshift 3, again, a galaxy at redshift 3, and this is observed with a filter Z, which determines the non-ionizing continuum. And to the right, you see a narrow band at 3,870, which it should encompass the ionizing continuum. You see a detection, and you would think, oh, wow, this galaxy has a lot of ionizing flux. But actually, the ionizing flux doesn't come from the redshift 3 source, but comes from the nearby source, which is just outside the red circles, okay? So, of course, these observations, at least the Z band, these are done with HST. These are done with HST with high spatial resolution. But imagine that these observations were done with, poorer spatial resolution. You would, confuse the galaxies, and then you would think, oh wow, there is a lot of ionizing continuum. This source is has a big escape of Lyman continuum radiation, but no, it's not true. It's just an interloper. So you need high spatial resolution observations to really, determine the ionizing correctly the ionizing continuum. So in fact, yeah, in this case, the flux that you see in the narrow band, you think it's ionizing continuum. No, it's not. It's not Lyman continuum radiation. And so at redshift 3, most sources seem to have very, very small escape fractions. So normally when we do this type of observations of single individual redshift 3 sources, so this source here is an exception because it has a very large escape fraction, and it's also very bright. But in most cases, when we do this type of observation, we see nothing in the Lyman continuum emission. And we see nothing both because sources have very, have very low escape fractions, and also because we are observing faint sources. And so sometimes what we try to do, so for example, here is a limit on the escape fraction on the y-axis versus our magnitude. And so you see there's lots of basically just errors. So what you see is upper limit. So you say, okay, sources have, escape fraction less than 0.1, less than 0.2, less than 0.01. Of course, for the brighter sources, you can, set more limiting, you can set better constraint. And for faint sources, yeah, you can just say, okay, this source has less than 20, 30% escape fraction. So one trick we try to do is actually do stacking analysis. So we stack all the UV continuum, and then we try to see whether in the the narrow the band that encompasses the ionizing radiation, we see some average signal. So in this way, we can probe deeper limits. Even so, in most cases, we see nothing. So for example, this was a work by Grazian some years ago, where they took about 70 sources in very narrow redshift range, so that the R band would encompass the non-ionizing continuum, and the U band would encompass the ionizing continuum. So what he did is just basically put all the flux together, and so you have this very bright source, say unique source, and he was hoping that something would pop up in the U band that would tell you that on average these 70 sources have maybe 5-6% ionizing leaking radiation. But in this case, it could just get, again, a limit. So this was just a deeper limit, and the limit was actually a few percent. So basically, these observations tell us that at redshift 3, most sources have very, very small escape fractions. So even if source, produce intrinsically a lot of ionizing radiation, most of this ionizing radiation stays inside the galaxy. So the ionizing radiation does not escape into the intergalactic medium. Another problem is that, the escape fraction is not a single quantity, okay? Because, the ionizing photons could come up, for example, from a region where there is no dust. So because galaxies are not monoliths, so they're not single entities, but they are, spatial distribution of stellar emission, spatial distribution of source. So there is also an isotropic Lyman continuum escape, which could be a common feature. And so in this recent work, for example, Xi and collaborators shown that there is Lyman continuum could come from regions that does not completely coincide with the stellar source. So again, this tells us that spatially resolved, so high spatial resolution is very, very important in this type of studies. And actually, this is also something that simulations tell us. So the escape fraction of ionizing radiation could vary also with direction, depending on where you look at the source. So if you happen to look at the source on a very clear pathway, you might see this, Lyman continuum radiation. But of course, we don't really look at sources in different directions. We can do this in simulations. And in simulation, you can look at the same source in different direction. And the same source will appear as a Lyman continuum leaker or not, depending on which channel you look at. And last but not least, again, simulations tell us that also escape fraction could vary with time. And so if you observe a galaxy and you don't see any escaping radiation, this might tell you that in this particular moment, there are no clear channels, but at earlier or later moments, of course, in the life of the source, there could be escaping radiation. So these are some, some of the models we make to understand this escape fraction. So these are some, say, schematic way in which you think, escape fraction, escaping radiation could escape from sources. And so you have basically two models in which you have in one the right, in the left model, you have the ionization bounded nebula with holes. Basically, the escaping radiation only gets out through these holes, through these channels that are created somehow in the interstellar medium. So in all plots here, you have a central ionizing source, which are the stars, and then you have H2 regions, which is the green stuff, and you have an outer layer of H1 gas, which is in gray. And in this case, in these models, you can see that from this, you have some channels, and then the diamond continuum and direct starlight come out of these channels, whereas when you have both H2 and H continuum, okay? And of course, you can put dust on top of these models, okay? And so when you put dust on top of these models, again, you have different behaviors in the ionization bounded nebula and in the density bounded nebula. So basically, in the ionization bounded model, the dust screen has no impact on the Lyman continuum, simply because the Lyman continuum will come out again through this channel. So here you see, I'm talking about the left model here. So this is the ionization bounded nebula with no dust. And then when you put dust, the channels are still free, right, of dust. And so there will be no impact on the Lyman continuum, okay? But there will be impact on the stellar light, because the stellar light comes out of the region where you now have the dust. Whereas in the dust density bounding nebula, the dust will impact both the stellar light, but also the nebular emission. So I will just now talk about the final challenge and then postpone everything to tomorrow, since I have only 2 minutes. So the final challenge is that the direct detection of ionizing radiation is impossible at redshift higher than 5 or 4.5 due to the very high IgM opacity. So far we talked about Lyman continuum emitters at redshift, say, 0 in the local universe. Remember, you need the HST. Then redshift 3, very, very difficult. We have a number of challenges, but we can do it. But what about the epoch of ionization? The epoch of ionization is where we need to measure the escape fraction, because we need to solve the famous equation, the ionizing budget. Well, unfortunately, we cannot measure the escape fraction exactly in the epoch of ionization, because the transmission of the intergalactic medium, it's very low. Basically, the IgM is completely opaque, and so there is no transmission of such sources, flux. So by definition, we are not able to measure this key ingredient of ionization for the galaxy in the epoch of ionization. And so this is a very, very major challenge. And so I think I will stop here, but tomorrow I will try to tell you how we're trying to somehow go around this challenge. And so I leave you with this slide, which basically tells you where we are now in the studies of Lyman continuum escape. We have a low redshift. We have several sources, about 100 sources, where we can study very well the escape of Lyman continuum emission and the physical properties. At redshift 3, where we still can measure the Lyman continuum sources, the Lyman continuum leakage, we have only about 10 individual solid detections. So as I told you, we give names because there are so few. One is, for example, the Sunburst arc, which is a very famous lens source. And then we have, of course, limits from the stacking analysis. And then we have this big question mark in the epoch of ionization. And so tomorrow morning, I will, tell you the ways we employ to kind of go around this big challenge. And I will stop here.
Thank you very much. Are there any questions before coffee? I know that's a big ask.
Okay. Email is also okay if you want to send emails.
I had a question actually.
Okay.
Sorry, I know I'm not the target audience, but I never understood the connection between like the Lyman continuum and then the Lyman alpha escape fraction. Some people have Lyman alpha escape fraction. Can they be related, or
I mean, they are definitely
Yeah.
related. And actually, I will show, well, actually, the first slide that I will show tomorrow is that there is a very observationally, empirically, there's a relation between the two emissions. And this is simply due to the fact that the conditions probably that favor the production and escape of the Lyman continuum and the Lyman alpha photons are very similar. If you have dust, at least in some models, will suppress Lyman continuum and also Lyman alpha. Not in all models, Lyman continuum, as I showed before. But, if you have, very young stars, they will produce a lot of Lyman continuum and a lot of Lyman alpha. So, the two emissions must be related somehow. And this is something that you do see from observations. But so I think it's more because, they escape through similar mechanismic conditions, and they're also produced by, more or less the same type of stars. And this is something that is very useful when we try to, have the indirect relations, as I will show tomorrow.
Thank you. Any questions for Lara? Okay, I think everyone wants coffee, so we'll see you tomorrow.
Okay, have a good coffee. Ciao.
Bye. All right.
So, Rosa, I will connect